Tonight, we're going to hold something that should not exist. Somewhere in our galaxy, right now, there is a single spoonful of matter that weighs more than every human being alive. 1 teaspoon, 1 billion tons, scooped from the corpse of a dead star, crushed so tightly the empty space inside its atoms is simply gone. Hold it in your hand, and it would not sit there. It would explode with the force of a nuclear bomb. This is a neutron star, the densest, most violent object the universe knows how to build. And tonight's question sounds simple. What would actually happen if a piece of one hit the Earth? The answer is stranger than you think, because it could never reach you as a teaspoon at all. By the end of tonight, you'll understand why and what these impossible objects really are. If these slow journeys out through deep space bring you a little calm at the end of the day, take a second to leave a like or subscribe. It genuinely helps these long nights reach other people looking for the same quiet. Now, let's begin. To understand the teaspoon, we first have to understand what a neutron star actually is. And to do that, we have to be careful, because the word dense is going to do a lot of work tonight. And it's a word we use far too casually. When we say a rock is dense, we mean it's heavier than it looks. When we say lead is dense, we mean a small block of it has a surprising heft. Lead is about 11 times denser than water. Gold is about 19 times denser than water. These are the densest ordinary things most of us will ever touch, and already they feel strange in the hand, too heavy for their size. A neutron star is not 11 times denser than water. It is not 19 times. It is roughly 100 trillion times denser than water. Take a second with that number, 100 trillion. Written out, that's a 1 followed by 14 zeros. There is no object on Earth, nothing you have ever held or seen or stood next to, that comes within a breath of it. The densest naturally occurring material you could ever encounter on this planet is still effectively empty space compared to the stuff a neutron star is made of. And that comparison, empty space, is more literal than it sounds. Everything around you, the chair, the floor, your own body, is made of atoms, and atoms are mostly nothing. If you took a single atom and blew it up to the size of a sports stadium, the nucleus at its center, the part that holds almost all the mass, would be about the size of a small marble sitting on the center line. Everything else, the entire rest of the stadium, is just empty space with a few electrons whispering around the edges. That is what solid matter is, a marble in a stadium. Repeated over and over, trillions upon trillions of times. The reason your hand doesn't pass straight through the table is not that the table is full, it's that the electrons in your hand and the electrons in the table push against each other and refuse to overlap. You have never actually touched anything in your life. You've felt the resistance of electric fields holding the emptiness apart. Now imagine you could switch that resistance off. Imagine you could crush the marble and the stadium down until the empty space was gone, until every nucleus sat shoulder to shoulder with the next, with nothing wasted in between. That is a neutron star. It is what you get when matter stops being mostly empty and becomes, for the first time, almost completely full. The mass of an entire star, more mass than our sun, squeezed until the emptiness is gone. And when the emptiness goes, the size collapses with it. Our sun is about 1.4 million kilometers across. You could line up 109 Earths along its face. Take that sun, take all of that mass, and crush out the empty space inside its atoms, and the whole thing collapses into a ball roughly 20 kilometers wide. 20 kilometers. That's it. The mass of a star compressed into something you could drive across in 20 minutes. A neutron star would fit comfortably inside most major cities. It would sit inside the ring road of London or stretch from one side of New York to the other, and it would weigh more than the sun. It helps to come at this density from a few different directions, because no single comparison can quite hold it. Picture the tallest mountain on Earth, Everest, all of its rock and ice and impossible weight. Now imagine compressing the entire mountain down until it fits inside a single sugar cube. That sugar cube is roughly as dense as neutron star material. Or take every car on the planet, more than 1 billion of them, and crush them all together until they fit in the bowl of a spoon. Or, as we said, take the whole of humanity, all 8 billion people, everybody that has ever stood in a crowd, and pack them into a space you could close your hand around. Each of these is just another way of saying the same impossible thing. The matter is so dense that the quantities stop feeling real, and yet it is real, sitting out there in the dark by the hundreds of millions. That is the object we're talking about tonight, a city-sized sphere with the mass of a star. And the teaspoon of material we started with, that billion-ton spoonful, is just one tiny scoop taken from a place where the entire universe has been folded down into almost nothing. Now, I said the figure was around 1 billion tons, and I want to be honest with you, because the exact number is harder to pin down than you might expect, and the reason why is itself part of the story. Depending on where in the star you take your teaspoon from and which careful estimate you trust, that spoonful might weigh as little as a few million tons or as much as several billion. A neutron star is not uniform. It gets denser the deeper you go. The matter near the surface is crushed. The matter at the core is crushed almost beyond description. So the honest answer is that a teaspoon weighs somewhere in the range of millions to billions of tons. And the fact that physicists argue about exactly where in that range it lands tells you something. We are dealing with matter so extreme that even our best descriptions of it come with a margin of uncertainty. But hold on to the simplest version. A teaspoon. 1 billion tons. More than all of humanity. That image is close enough to the truth to keep you up at night. And here is the first uncomfortable question. How does the universe make something like this? Matter does not want to be this dense. Every atom in your body is, right now, holding itself apart, electrons refusing to be pushed into the nucleus. It takes an almost unimaginable force to overrule that, to crush atoms until they stop being atoms. There is only one process in nature violent enough to do it, the death of a giant. A neutron star begins its life as an ordinary star, but a very large one. Our sun is a perfectly average star, and the sun will never become a neutron star. It simply isn't big enough. To make a neutron star, you need a star at least 8 times the mass of the Sun, and often far more. The giants, the ones that burn hot and bright and fast and die young. For most of its life, a star is a balancing act, a quiet war that goes on for millions of years without a winner. On one side, gravity, constantly trying to crush the star inward to pull all that mass toward the center. On the other side, the heat of nuclear fusion in the core pushing outward, holding the star up. Gravity pulls in, fusion pushes out, and as long as those two forces stay matched, the star is stable. It shines. It holds its shape. It lives. That balance is the only thing keeping the star from collapsing, and it depends entirely on the star having fuel to burn. In the core, the star fuses hydrogen into helium, and that reaction releases the energy that pushes outward against gravity. But fuel runs out. When the hydrogen in the core is gone, the star starts fusing helium into carbon. When the helium runs low, it fuses carbon, then neon, then oxygen. Each stage burns hotter and faster than the last. A massive star can spend 10 million years fusing hydrogen, but only a few hundred years fusing the heavier elements near the end. The fire is racing through the last of its fuel, and it builds the star in layers, like an onion. Hydrogen burning in the outer shells, heavier and heavier elements as you move inward, until, at the very center, the star fuses silicon into iron. Iron is where the music stops. Every fusion reaction up to this point has released energy. That's the whole point. That's what holds the star up. But iron is different. Iron is the most tightly bound nucleus there is. You cannot fuse iron into anything heavier and get energy back out. In fact, fusing iron costs energy. It takes more than it gives. So when the core of a massive star turns to iron, the fire goes out. Not slowly, all at once. The core has been producing the outward push that fights gravity. And now, for the first time in the star's entire life, that push is gone. There is nothing left to hold the star up. And gravity has been waiting for this moment for 10 million years. What happens next happens faster than you can think. The iron core, about the size of the Earth but containing more mass than the Sun, collapses, and it doesn't drift inward gently. It falls. The outer edge of that core caves toward the center at speeds approaching 70,000 kilometers per second. That's nearly a quarter of the speed of light. An object the size of our entire planet collapsing inward in less than a single second. Think about how violent that is. The whole core falling almost as fast as light itself, all of it racing toward a single point. As it collapses, the matter is crushed harder than anything in the star's history. And here is where the atoms themselves begin to break. Under normal conditions, electrons keep their distance. They refuse to be pushed into the nucleus. This is the same stubborn resistance that keeps your hand from passing through a table. It's called degeneracy pressure, and it is one of the most reliable rules in all of physics. Electrons do not like to be crowded, but the collapse of a stellar core is not a normal condition. The inward force becomes so overwhelming that it overrules the rule. The electrons are crushed directly into the protons inside the nuclei, and when an electron and a proton are forced together, they merge. They become a neutron, and they release a ghostly particle called a neutrino. This is the moment the neutron star gets its name. In the space of less than a second, the core stops being made of ordinary atoms. The electrons are gone, swallowed into the protons. What's left is a sea of neutrons packed together with no empty space between them at the density of an atomic nucleus. The emptiness inside matter has been erased. The marble has filled the entire stadium, and the collapse finally stops, because now the neutrons themselves refuse to be crowded any further. Neutrons have their own version of degeneracy pressure, and it is far more stubborn than the electrons. The infalling core slams into this wall of neutron resistance, and in an instant, it rebounds. It bounces. That rebound sends a shockwave tearing back out through the star. The outer layers, millions of times the mass of the Earth, are still falling inward, and they meet this outward shock, helped along by the flood of neutrinos pouring out of the new core. The result is one of the most violent events in the universe, a supernova. For a few weeks, the dying star outshines its entire galaxy. A single star, blazing brighter than 100 billion others combined. The outer layers are blasted into space at thousands of kilometers per second, seeding the cosmos with the heavy elements forged in the star's long life. The calcium in your bones, the iron in your blood, much of it was made inside a star and scattered by an explosion exactly like this one. You are, quite literally, made of the debris of dead stars. It's hard to overstate the energy involved. In the few seconds of that collapse and explosion, a supernova releases more energy than our sun will produce in its entire lifetime, across 10 billion years of steady burning, all of it in seconds. Most of that energy doesn't even go into the light we see or the blast we measure. The overwhelming majority is carried off invisibly in a flood of those ghostly neutrinos pouring out of the collapsing core. For a brief moment, a single dying star can shine in neutrinos brighter than every other star in the observable universe combined. We see only the faint outer glow of an event whose true violence is almost entirely hidden from us. But we're not here for the explosion, we're here for what it leaves behind. In the center of all that fury, where the core bounced and held, a new object sits. The neutron star, 20 kilometers across, more massive than the sun, spinning, glowing, almost unimaginably hot. It has just been born in the most violent way nature knows, and it will outlast the explosion that made it by billions of years. And here is something extraordinary. We have very nearly watched this happen. Once. In February of 1987, a star exploded in the Large Magellanic Cloud, a small companion galaxy to our own, about 160,000 light-years away. It was the closest supernova we had observed in nearly 400 years, since before the invention of the telescope. And we did not just see it. We felt the collapse itself through the one messenger that escapes from the very center. Remember that when the core collapses and protons and electrons merge into neutrons, they release neutrinos, those ghostly particles. an almost unimaginable number of them carrying away the vast majority of the energy of the collapse. Neutrinos barely interact with anything. They pass through stars, through planets, through you, by the trillions every second without touching a thing. And because they interact so weakly, they escape from the heart of the dying star immediately, while the light is still trapped, fighting its way out through the exploding layers above. So, the neutrinos arrive first. A few hours before the light of that 1987 supernova reached us, a handful of neutrino detectors buried deep underground on Earth registered a tiny burst. In total, across 3 detectors, around 24 neutrinos in a flash lasting less than 13 seconds. 24 particles out of a flood of uncountable trillions that swept through the entire planet in that instant. And those couple of dozen specks were our direct detection of a stellar core collapsing into a neutron star 160,000 light-years away. We had caught the actual birth, not by its light, but by the ghosts pouring out of its center. For decades afterward, though, there was a mystery. We were fairly sure that collapse should have left a neutron star behind, but we couldn't find it in the wreckage. The remnant cloud was too thick with dust to see through. And then, only recently, the James Webb Space Telescope peered into the heart of that expanding debris and found the signature at last. Something at the center was bombarding the surrounding gas with intense radiation, exactly what a young, hot neutron star would do. After nearly 40 years, the object whose birth we detected in a 13-second whisper of neutrinos was finally confirmed to be sitting there, glowing in the dark, exactly as the theory promised. That is as close as we have ever come to standing in the room when a neutron star is made. A couple of dozen ghost particles and, decades later, a telescope finding the newborn in the smoke. Everything we find strange about a neutron star, the density, the teaspoon, the impossible weight, comes from this single moment. It was forged in a collapse, moving at a quarter of the speed of light. It was crushed by the full weight of a star falling on itself. That is the only kind of force in the universe powerful enough to overrule the stubbornness of atoms and squeeze matter into this state. Nothing gentler could ever do it. And that's the first clue as to why a teaspoon of it could never simply sit in your hand. It took the death of a giant to make this matter. It would take nothing less to keep it. And there is a knife edge hidden in all of this, a line between 2 completely different fates. The collapsing core stops and becomes a neutron star only if its mass falls within a specific window. Below a certain mass, the neutrons hold. The star stabilizes. But push past the upper limit, somewhere between 2 and 3 times the mass of the Sun, and not even the neutrons can win. The collapse doesn't stop. It continues past the neutron star stage, past every form of resistance matter can offer, and it becomes a black hole. So a neutron star is the densest thing in the universe that is still, technically, a thing. One small step more massive, and it would vanish behind an event horizon and stop being matter at all. The neutron star sits right at the edge, the last stable object before the laws of physics give up entirely, And to understand just how close to that edge it sits, we have to go inside. If you could cut a neutron star in half and look at its structure, you would find that it is not a uniform ball of neutrons. It has layers, like the Earth has a crust and a mantle and a core. Except every layer of a neutron star is a place where matter is doing something it does nowhere else in the universe. Let's travel down through it, from the outside in. The very outermost edge is the atmosphere, and it is almost nothing. On Earth, our atmosphere reaches up for hundreds of kilometers. The atmosphere of a neutron star is perhaps a few centimeters thick, a thin skin of hot plasma, mostly hydrogen and helium, lying over the surface. The gravity is so strong that it crushes the entire atmosphere down into a layer thinner than your hand. Below that, there may be an ocean, also only centimeters deep, of liquid metal. Then you reach the crust, and the crust of a neutron star is one of the strangest places imaginable. The outer crust is a solid lattice of atomic nuclei packed into a crystal far more rigid than anything on Earth. This material has been measured, in a sense, by watching how neutron stars behave, and the conclusion is staggering. The crust of a neutron star is thought to be around 10 billion times stronger than steel. It is the strongest known material in the universe. A solid shell, only a kilometer or two thick, but stronger than steel by a factor of 10 billion, wrapped around a sphere with the mass of the sun. And as you push deeper into that crust, the nuclei start to change. The pressure climbs so high that the atoms can no longer hold their normal shape. Remember, electrons are being squeezed toward the nuclei, and neutrons are being squeezed out of them. The nuclei become bloated with extra neutrons, swollen and unstable, shapes that could never exist on Earth for more than a fraction of a second. Deeper still, and something remarkable happens. The nuclei stop being separate balls at all. They are crushed so close together that they begin to merge and deform. And physicists have given the results a strangely gentle set of names. They call it nuclear pasta. Near the bottom of the crust, the pressure squeezes the nuclear matter into long tubes, like spaghetti. Push deeper, and the tubes flatten into sheets, like lasagna. The matter is being kneaded by gravity into shapes because the forces pulling it together and the forces pushing it apart have reached a strange and delicate standoff. Spaghetti, lasagna, then a structure full of holes, like Swiss cheese. It sounds almost comforting, these kitchen names. But this is matter under pressures that would vaporize a planet, arranging itself into forms we can barely simulate on our most powerful computers. The nuclear pasta layer may be the strongest, stiffest material that exists anywhere in reality. Try to sit with how strange that is. We tend to think of the inside of a star as a place of fire and gas, churning and formless. But the outer body of a neutron star is solid, rigid, a crystal of crushed nuclei, organized into shapes, layered from sheets to tubes to a honeycomb of holes, each form appearing at its own precise depth as the pressure climbs. It is more like the inside of a gemstone than the inside of a star, except a gemstone 10 billion times stronger than steel, holding back the weight of a sun. And this matters for more than wonder. It is this incredible rigidity that lets the crust build up stress and then crack, producing the star quakes we talked about, and it is the breaking and resettling of this crystal that may lie behind some of the most violent flares we see. The strength of that strange, layered shell is written into the light these stars send us. We are, in a sense, reading the crust of a dead star by the way it occasionally shatters, and then, beneath the crust, the pasta dissolves entirely, and you enter the heart of the star. This is the outer core, and here matter has given up almost all pretense of being made of atoms. It is a sea of free neutrons, with a small scattering of protons and electrons mixed in. Neutrons, packed together at the density of an atomic nucleus, but spread across kilometers instead of trapped inside a single atom. It behaves like a liquid, a neutron liquid with no friction at all. Because here is something extraordinary. The interior of a neutron star is thought to be a superfluid, a state of matter that flows with zero resistance, swirling forever without slowing down. And mixed into it, the protons are thought to form a superconductor carrying electric current with no loss whatsoever. The inside of a neutron star may be the largest superfluid in the universe, an ocean of frictionless neutrons kilometers deep, held under a crust of the strongest material in existence, all of it spinning. We will come back to that spin, because it produces some of the most precise signals in all of astronomy. It's hard to convey the pressure that creates all of this, but try holding the comparison in your mind. At the center of the Earth, the pressure is already crushing, millions of times the pressure of the air around you, enough to keep iron solid at temperatures hotter than the surface of the sun. The pressure at the center of a neutron star is greater than that by a factor so large there is no familiar word for it. It is the pressure of more than a sun's worth of mass, all pulling inward, focused down onto a single point. Nothing you could build, no vault, no diamond, no engineered material could exist there for the briefest instant. Everything we understand about how matter holds its shape simply stops applying. And matter, pushed that far, does the only thing left to it. It changes into something we have never seen. And then at the very center, the inner core, we reach the edge of human knowledge. Nobody knows for certain what is at the center of a neutron star. We cannot recreate these pressures in any laboratory. We cannot see inside. The density at the core may be several times higher even than the density of an atomic nucleus, and at those pressures the neutrons themselves may begin to break down. Remember that neutrons are not the smallest things in nature. A neutron is made of 3 smaller particles called quarks, normally bound so tightly that they can never be pulled apart. But in the core of a neutron star, the crushing may be so severe that the neutrons dissolve and their quarks are set loose, free to roam in a way they cannot anywhere else in the cosmos. This would be a new state of matter entirely, quark matter. Some physicists wonder whether the densest neutron stars might have cores made of this strange, liquid soup of fundamental particles. There may even be objects out there that are entirely quark stars, denser still than ordinary neutron stars, but we have never confirmed one. Some physicists have taken the idea even further into genuinely unsettling territory. They have speculated about a form of matter, sometimes called strange matter, that might be even more stable than ordinary matter once it forms in these extreme conditions. If such a thing existed, the thinking goes, it might be the true ground state of matter, the form everything would prefer to be in, if only it could get there. These are speculations at the very frontier of physics, unproven and debated, the kind of ideas that live in the gap between what we can calculate and what we can observe. But that gap is exactly where neutron stars sit. They are the one place in the universe where matter is squeezed hard enough that these questions stop being abstract and start being something that might actually be happening right now in the hidden cores of stars we will never crack open. The deepest mysteries about what matter is may be locked inside the most crushed objects that matter can become. The honest truth is that we do not know. The center of a neutron star is one of the last genuinely hidden places in physics. We can describe the journey down through the atmosphere, the ocean, the crust, the pasta, the superfluid sea. And then at the final step, we reach a question mark. The pressures become so extreme that our equations stop agreeing with each other, and we are left guessing at the nature of matter pushed to its absolute limit. What we do know is this: every layer we just traveled through is held in place by gravity. The crust, the pasta, the superfluid, the mysterious core, all of it exists only because the star is crushing itself inward with the weight of more than a sun. Take any piece of it away from that crushing pressure, and it would no longer be crust, or pasta, or superfluid. It would be unbound, free, and it would react to that freedom with violence. This is the deeper answer to our teaspoon. We tend to imagine scooping out a spoonful of neutron star the way you'd scoop ice cream, as if the material is just sitting there waiting to be lifted. But the material isn't sitting there at all. It is being held every instant by a gravitational vice stronger than anything you can picture. The teaspoon of matter is not a solid lump with a fixed weight. It is a piece of a system in extreme tension, like a coiled spring compressed to a fraction of its length, waiting. Lift it out, and you release the spring. We will follow exactly what happens when you do that a little later tonight. But first, we need to stand on the surface of this object, because the inside is strange beyond imagining, and the surface, the place where this city-sized sphere meets the rest of the universe, is where the strangeness becomes truly violent. Let's start with gravity, because gravity is the whole story here, and on the surface of a neutron star, gravity does things that break your intuition completely. On Earth, if you drop something, it accelerates toward the ground. We've all felt it. It's gentle enough that we can catch a falling cup, gentle enough that a person can fall over and stand back up. The gravity at Earth's surface is the only kind of gravity our bodies have ever known. The gravity at the surface of a neutron star is roughly 100 billion times stronger. That number is almost meaningless said out loud, so let's make it real. On Earth, you weigh whatever you weigh. Step onto the surface of a neutron star and you would weigh as much as a mountain range. Your body, the same body, would be pressed down with a force so immense that no structure made of atoms could survive it. You would not stand on a neutron star. Nothing stands on a neutron star. You would be flattened instantly into a layer of atoms smeared across the surface, thinner than a sheet of paper, because the gravity is simply too strong for the bonds in your body to resist for even an instant. And it gets stranger, because that gravity doesn't just crush, it accelerates. Drop an object from 1 meter above the surface of a neutron star, 1 single meter, and by the time it reaches the surface, it would be traveling at around 2,000 kilometers per second from a 1 meter drop. On Earth, a 1 meter fall is nothing, a dropped book, a stumble. On a neutron star, that same fall would accelerate the object to a speed that could cross an entire country in a second or two. The energy released when it struck would be comparable to a nuclear weapon. A single marshmallow dropped onto a neutron star from just above the surface would hit with the force of hundreds of atomic bombs. Take a moment with that. A marshmallow, a soft, harmless thing. Released from 1 meter up, it would strike the surface with the energy of a city-destroying weapon, simply because of how hard this object pulls. This is what it means for gravity to be 100 billion times stronger. Every gentle thing becomes a weapon. Every small fall becomes a catastrophe. The neutron star takes the most ordinary physics, a dropped object, and turns it into violence, because the numbers have been pushed so far past anything in our experience. Now look at the surface itself. With gravity this overwhelming, the neutron star is the smoothest, roundest object known to exist. Any bump, any irregularity is pulled down relentlessly toward a perfect sphere. On Earth, our tallest mountain rises nearly 9 kilometers. On a neutron star, the tallest possible mountain, a ripple in that crust, 10 billion times stronger than steel, might be a few millimeters high, perhaps less. The entire surface of a neutron star varies by no more than the thickness of a few sheets of paper. A ball 20 kilometers across, smoother than anything human hands have ever polished. And those tiny mountains matter more than you'd think, because when the crust shifts, even by a fraction of a millimeter, the result is a starquake. The rigid crust cracks and resettles under the impossible strain, and the whole star shudders. A starquake on a neutron star can release more energy in 1/10 of a second than our sun puts out in tens of thousands of years. The largest one ever detected from a distant magnetic neutron star struck Earth's atmosphere from 50,000 light-years away and still measurably disturbed it. A crack a few centimeters long on a star halfway across the galaxy, reaching out and touching our planet. Then there is the light. And here the neutron star does something to space itself. The gravity is so intense that it bends the path of light around the star. We're used to thinking of light as traveling in straight lines, and it does, but gravity curves the space that light travels through. Near a neutron star, that curve is so severe that light coming from the far side of the star, the side facing away from you, gets bent around the edges and into your eyes. You would be able to see part of the back of the star. The surface that should be hidden behind the horizon is lifted into view by the bending of space. If you could somehow look at a neutron star up close and survive, you would see more than half of its entire surface at once, wrapped toward you by gravity, the hidden hemisphere curling into sight around the edges, and time itself slows down there. The stronger the gravity, the slower time runs, and near a neutron star, the effect is dramatic. A clock sitting on the surface would tick noticeably slower than a clock far away in space. If you watched from a safe distance, events on the surface would appear to drag, stretched out by the gravity. Time, light, weight, the shape of space, all of it distorted by the same simple cause: too much mass pressed into too small a space. It's worth pausing on that slowing of time because it is not a trick of perception. It is real, and we rely on the same effect every day in a much gentler form. The satellites that run the positioning system in your phone orbit high above the Earth, where gravity is slightly weaker, and their clocks tick very slightly faster than clocks on the ground. The difference is tiny, a few millionths of a second a day, but if engineers did not correct for it, your navigation would drift off by kilometers within hours. That is gravity bending time here in our calm corner of space. Now take that effect and crank it up by a staggering amount. On the surface of a neutron star, time runs slow enough that if you could somehow watch a clock down there from far away, you would see it lagging visibly behind your own minute after minute, hour after hour. The light climbing up away from the surface even loses energy doing it, stretched and reddened as it fights against the gravity, arriving to you wearier than it left. The neutron star doesn't just sit in space, it dents it. We should talk about the heat, too, because a neutron star is born in fire and stays burning for a very long time. A young neutron star can have a surface temperature of 1,000,000 degrees or more. Even the nearest one to us, an old, quiet star that has been cooling for hundreds of thousands of years, still sits at a surface temperature of over 400,000 degrees Celsius. For comparison, the surface of our Sun is around 5,500 degrees. This cold, dead, ancient remnant is still nearly 100 times hotter on its surface than the Sun. It is only called cold because, for a neutron star, 400,000 degrees counts as having cooled down. And because it is so hot, most of a neutron star's light is not the kind your eyes could ever see. An object glowing at hundreds of thousands or millions of degrees shines most brightly, not in visible light, but in X-rays, the same high-energy radiation used to photograph the bones inside your body. To human eyes, a neutron star would be a faint, dim point, if you could see it at all. But to an X-ray telescope in orbit above our atmosphere, the sky tells a different story. It is dotted with these fierce, hot points of light, neutron stars and the disks of matter falling onto them, blazing in a part of the spectrum we are blind to. There is an entire layer of the universe written in X-rays that we only learned to read in the last few decades, and much of what glows in it is the crushed remains of dead stars. The night sky you can see is only part of what is actually there, so picture the surface, now, fully. A perfect sphere, 20 kilometers wide, smoother than glass, glowing at hundreds of thousands of degrees, wrapped in a gravity so strong it bends the light from its own far side into view, slows down time, and would crush anything that approached into a smear of atoms. A marshmallow would land like a nuclear bomb. A grain of dust would arrive like an artillery shell. This is the doorstep of the object. And we still haven't touched the thing that makes neutron stars famous, because most of them are not sitting quietly in space. They are spinning faster than you can possibly imagine. And as they spin, they sweep the galaxy with beams of energy as regular as a heartbeat. To understand why a neutron star spins so fast, think about a figure skater. When a skater pulls their arms in close to their body, they spin faster. It's the same amount of motion packed into a smaller space, so it speeds up. Physicists call this the conservation of angular momentum, but you've seen it your whole life. Arms out, slow. Arms in, fast. Now apply that to a dying star. The original star was enormous, more than 1 million kilometers across, and it was rotating slowly, taking perhaps weeks to turn once. Then the core collapsed, from the size of the Earth down to 20 kilometers in less than a second. The skater didn't just pull her arms in, she pulled them in by a factor of tens of thousands. And all of that rotation, all of that spin had to be conserved. So as the core shrank, it sped up, and up, and up. The result is almost impossible to picture. A newborn neutron star, an object more massive than the Sun, can spin on its axis dozens of times every second. Some of them spin hundreds of times per second. The fastest neutron star ever found rotates 716 times every single second. Say that slowly. A ball, the mass of a star, the size of a city, turning completely around more than 700 times in the space of 1 second. The surface at its equator is moving at a significant fraction of the speed of light. If it spun very much faster, it would begin to tear itself apart. An object with the mass of the Sun, spinning faster than the blades of a kitchen blender. There is nothing in human experience to compare it to, and yet these objects keep that spin with a regularity so precise it rivals the best clocks ever built. Which brings us to how we found them in the first place, and it's one of the great stories in the history of science. In the autumn of 1967, a young graduate student named Jocelyn Bell was working in Cambridge, in England, studying signals from space using a radio telescope she had helped to build by hand, stringing wire across acres of field. She was poring over data printed on long rolls of paper, hundreds of meters of it, reading the squiggles by eye. And on the 28th of November, she noticed something she would later describe as a bit of scruff. A small, repeating signal that didn't look like anything she'd been taught to expect. She measured it carefully, and what she found was a pulse, a regular beat, arriving once every 1 1/3 seconds with astonishing precision. Tick, tick, tick. Steadier than a clock, coming from a fixed point in the sky, far beyond our solar system. It was so regular that, for a short while, the team genuinely wondered if it could be a signal from another civilization. They half-jokingly labeled the source LGM-1 for little green men, because nothing in nature was supposed to be able to keep time like that. What natural object could possibly tick with the steadiness of a machine? The answer, within months, turned out to be stranger than aliens. It was a neutron star, a spinning one. And the reason it pulsed was beautiful in its simplicity. A neutron star has an intensely powerful magnetic field, and that field channels beams of radiation out from its magnetic poles like two searchlights pointing in opposite directions. But the magnetic poles are usually not lined up with the axis the star spins around, just as Earth's magnetic North Pole doesn't sit exactly at the geographic North Pole. So as the neutron star rotates, those beams sweep around and around, like the beam of a lighthouse. And if one of those beams happens to sweep across the Earth, we see a flash, then nothing. Then, as the star turns again, another flash, a pulse, arriving with every rotation. That's why we call them pulsars. A pulsar is simply a spinning neutron star whose beam happens to point our way once per turn. The pulse isn't the star turning on and off. The star is shining steadily. We are just catching the beam each time it sweeps past us, like standing on a dark coast and seeing the lighthouse flash as it comes around. Jocelyn Bell had discovered the first one, and in doing so, she had found the first direct evidence that neutron stars, predicted decades earlier but never seen, were actually real. The prediction, remarkably, went all the way back to 1934, when two astronomers, Walter Baade and Fritz Zwicky, proposed that supernovae might leave behind tiny, impossibly dense stars made of neutrons. They made that suggestion only a couple of years after the neutron itself had been discovered. For 33 years it remained a wild idea on paper, and then a graduate student reading rolls of chart paper proved them right. Today we know of thousands of pulsars, and their timing is so reliable that we use them almost like cosmic clocks. The most stable ones keep time so well that over years they rival atomic clocks here on Earth. Astronomers are using networks of them right now to try to detect gravitational waves washing through our galaxy, watching for the faint, coordinated wobble that a passing ripple in space would imprint on dozens of these distant, ticking beacons at once. A dead star, found by accident on a roll of paper, has become one of the most precise measuring instruments we have. But the magnetic field that makes a pulsar shine is itself worth stopping on. Because for some neutron stars, the magnetism is not just strong, it is the strongest thing in the known universe. A typical neutron star has a magnetic field trillions of times stronger than the Earth's. That alone is extreme. But a special class of neutron stars called magnetars take it to a level that is genuinely hard to write down. A magnetar's magnetic field can be 1,000 trillion times stronger than Earth's. There is nothing else like it anywhere. These are the most magnetic objects that exist, and a field that's strong does not just push compass needles around. It reshapes matter itself. Get within 1,000 kilometers of a magnetar, and the field would be so intense that it would distort the atoms in your body, stretching them into thin, useless needles, pulling your chemistry apart. The bonds that hold molecules together rely on the shapes of atoms, and a magnetar would deform those shapes until biology simply could not function. You would be unmade not by heat, not by radiation, but by magnetism alone, long before you ever reached the surface. When a magnetar's field shifts, When the crust cracks and the magnetism suddenly rearranges, it releases a flare of energy so enormous that it can be detected across the entire galaxy and beyond. In 2004, a flare from a magnetar tens of thousands of light-years away reached Earth and, for a fraction of a second, disturbed our upper atmosphere, the same atmosphere that shields us from the sun. A dead star, half a galaxy away, reaching across the void and brushing against our sky. These magnetars may also be behind one of the strangest mysteries in modern astronomy. For years, telescopes have been catching fast radio bursts, immense flashes of radio energy that last 1,000th of a second and arrive from across the universe, releasing in that instant as much energy as the sun pours out in days. For a long time, nobody knew what could possibly produce them. Then, in April of 2020, a magnetar in our own galaxy, about 30,000 light-years away, suddenly flared and released exactly such a burst. The first fast radio burst ever traced to a source we could name, and the source was a neutron star. We still don't know if magnetars explain all of these bursts, but we now know they can produce them, which means some of the brightest radio flashes in the entire cosmos are coming from the cracking, shifting, magnetic fields of dead stars 20 kilometers wide. So this is the spinning, magnetic reality of a neutron star. It turns hundreds of times a second. It sweeps the cosmos with lighthouse beams. It carries magnetism strong enough to tear atoms apart from 1,000 kilometers away, and it keeps time through all of it with a steadiness that fooled its discoverers into thinking they'd heard from another world. All of this from a ball 20 kilometers across, all of it powered by the same crushing density that fills our teaspoon. Before we ask where these objects are, there's one more behavior we have to see, because not every neutron star drifts alone and quiet. Some of them are feeding. Picture a neutron star with a companion, an ordinary star orbiting close by, still alive, still burning. The neutron star's gravity is so overwhelming that it can reach across the gap between them and begin to pull gas off the surface of its companion. The outer layers of the living star are stripped away, drawn toward the neutron star in a long, glowing stream. But the gas cannot fall straight in. Because both stars are orbiting, the stolen material swirls into a flat, spinning disk around the neutron star, like water circling a drain. This is called an accretion disk, and as the gas spirals inward, it is squeezed and heated by friction and by the neutron star's ferocious gravity. By the time it nears the surface, the gas has been heated to millions of degrees, and it blazes not in visible light, but in X-rays. Some of the brightest X-ray sources in the entire sky are neutron stars feeding on a companion, glowing across thousands of light years with the heat of matter falling to its death. And the falling matter does something violent when it lands. It piles up on the surface layer upon layer of stolen gas, compressed by that 100 billion times gravity. The pressure and heat build until, suddenly, the whole layer ignites in a runaway thermonuclear explosion across the surface of the star. A burst of nuclear fire wrapping around a sphere 20 kilometers wide in a flash that lasts seconds and outshines everything around it. These are called X-ray bursts, and some neutron stars produce them again and again every few hours or days as they slowly build up and then detonate the fuel they've stolen. A star eating another star and burping fire. The feeding does something else too. As the gas spirals in, it carries momentum, and it spins the neutron star up faster and faster, like water spinning a wheel. An old, slow neutron star that has nearly stopped pulsing can be given a second life this way, spun back up to hundreds of rotations per second. These are the recycled pulsars, the millisecond pulsars we met earlier, the most precise, natural clocks in the universe. They are old stars, reborn fast by feeding on a neighbor. The steadiest timekeepers we know are, in a sense, the ones that found something to eat. And some of them do not stop at feeding. Some of them destroy the very companion that gave them their second life. There is a class of these recycled pulsars with names that tell you everything. Astronomers call them black widows and redbacks after the spiders that devour their mates. Once one of these neutron stars has been spun up to hundreds of rotations a second, it pours out a furious wind of particles and radiation, and that wind turns on the companion star that fed it. It begins to blast away the companion's outer layers, stripping the star down, evaporating it from the outside in. The pulsar, having taken what it needed, now slowly burns its partner away. In some of these systems, the doomed companion has already been reduced to a fraction of the mass of a planet, a wisp of a star being boiled off into space. And if the process runs to its end, the companion may be erased completely, leaving the pulsar alone again, spinning fast, with no trace of the star it consumed to get there. A dead star that ate its way back to life and then destroyed the thing that saved it. Now imagine, just for a moment, that you could approach one of these objects and somehow survive the journey. What would you see? At first, from far away, perhaps nothing but a faint, hot point of light, far too small to make out. But as you drew closer, the strangeness would begin. Light from behind the star would curl into view around its edges, so the small sphere would seem to swell, showing you more of itself than should be possible. Your clocks would slow against the clocks back home. If the star were pulsing, you would be falling toward a lighthouse turning hundreds of times a second, its beams sweeping past you faster than any strobe. And the gravity would build, gently at first, then with a steepness no human structure could survive, until, in the final instant, the same force that holds the teaspoon together would take hold of you, and you would become part of the surface. We will never make that journey. But the physics lets us imagine standing at the doorway of the most extreme object that still counts as matter. And here is something that should give you a quiet kind of wonder. We can actually see the place where one of these objects was born. And we have a written record of the night it happened, kept by people who had no idea what they were looking at. In the year 1054, almost 1,000 years ago, astronomers in China recorded the sudden appearance of a brilliant new star in the constellation we now call Taurus. They called it a guest star, a star that arrives and then departs. It blazed into the sky on the 4th of July, 1054, and it was so bright, around 4 times brighter than the planet Venus, that for 23 days it was visible in broad daylight. At night, it lingered for nearly 2 years before slowly fading from view. The records were kept in China and echoed in Japan, careful notes of a light that came from nowhere and would not leave. What those astronomers were watching, without any way of knowing it, was a supernova, a massive star tearing itself apart 9,000 years of distance away. The light of its death had been traveling toward Earth for all that time and finally arrived in the summer of 1054. And today, if you point a telescope at that exact spot in Taurus, you see what they left behind. A vast, glowing cloud of shredded gas, still expanding outward after 1,000 years, lit from within by a tangle of color. We call it the Crab Nebula. It sits about 6,500 light-years away, and it is one of the most studied objects in the sky. But the truly remarkable thing is at its very center, because there, in the heart of the wreckage, sits a neutron star. The crushed core of the star that exploded in 1054, exactly where the theory says it should be. It is a pulsar, and it spins 30 times every second, sweeping its beams across us with each turn, a rhythm we have been tracking for decades. The guest star the Chinese astronomers watched in daylight 1,000 years ago is still there, transformed, beating like a heart in the middle of the cloud it created. A direct line connects a note scratched onto paper in the 11th century to one of the densest objects we know of today. The death was witnessed. The remnant remains. These objects can do something else that sounds, frankly, impossible. They can have planets. In 1992, astronomers studying a pulsar called PSR B1257, about 2,300 light-years away, noticed that its incredibly steady ticking was slightly off. The pulses arrived a touch early, then a touch late, in a regular pattern. Something was tugging on the neutron star, ever so gently, shifting its position back and forth. And when they worked through the math, the answer was extraordinary. The pulsar had planets, worlds orbiting a dead star, betraying themselves by the tiny gravitational pull they exerted on its perfect rhythm. Those were the first planets ever confirmed beyond our own solar system. The very first exoplanets humanity ever found were not orbiting a warm, sun-like star. They were circling the corpse of one. A neutron star, with a small family of worlds wheeling around it in the dark, detected only because the dead star kept time so precisely that even a planet's faint tug showed up in the beat. There is something haunting in that. The first other worlds we ever proved existed are orbiting a place where any ordinary life is unthinkable. Bathed in radiation, lit by a lighthouse that turns hundreds of times a minute. This precision, this incredible steadiness, is also how we measure the neutron stars themselves. We cannot fly to one, we cannot land on it and take readings, but we can watch them with exquisite care from here. There are instruments built for exactly this, including one mounted on the International Space Station, watching neutron stars in X-rays, timing the hotspots on their surfaces as they rotate, trying to pin down precisely how big they are and how their mass relates to their size. Because that relationship, how much a neutron star weighs against how wide it is, holds the answer to the deepest, unsolved question about them. What is the matter at their core actually made of? Every careful measurement narrows the possibilities, ruling out some ideas about that hidden center, allowing others. We are, slowly, feeling our way toward the heart of an object we can never open. And every so often the neutron stars give us a clue from the inside on their own. A pulsar will be ticking along, gradually slowing over years, and then suddenly, without warning, it speeds up just a little in an instant. A glitch. These tiny, sudden spin-ups are thought to be the signature of that frictionless superfluid deep inside the star, abruptly handing some of its motion to the crust, a hidden ocean making itself felt at the surface. We cannot see the superfluid, but we can watch it nudge the whole star, and in that nudge, read something about a sea of neutrons buried under the strongest crust in the universe. The star, in its own way, is telling us what is inside it. So where are they? It's natural to wonder, once you know these things exist, just how far away the nearest one is, whether we are anywhere near such an object. Our galaxy, the Milky Way, is thought to contain somewhere between 100 million and a billion neutron stars. That is an astonishing number. Hundreds of millions of dead stellar cores drifting through the galaxy, the remnants of every massive star that has lived and died over billions of years. Most of them are old and cold and silent now, no longer pulsing, just dark spheres of impossible density coasting between the stars. For every brilliant pulsar we can detect, there are many more we will never see, because their beams don't point our way, or because they stopped beaming long ago. That is a quietly haunting thought. The galaxy is full of these objects, and most of them are invisible to us. They drift between the stars, cold and dark and silent, no longer pulsing, giving off only the faintest glow of ancient heat, far too dim to notice unless they happen to pass in front of something. There could be neutron stars closer to us than the 400 light-years of our nearest confirmed one, and we simply would not know, because a dead, dark neutron star the size of a city is almost impossible to spot across the vastness of space. The galaxy we picture, full of shining stars, is also quietly haunted by hundreds of millions of these dense, dark cinders, the buried remains of every giant that ever lived and died, coasting forever through the spaces in between. We see the living stars. We rarely see the graves. The nearest one we have found sits about 400 light-years away, in the direction of a southern constellation called Corona Australis, the Southern Crown. It carries the unromantic name RxJ11856. It is an isolated neutron star, no longer pulsing, discovered only because it glows faintly in X-rays with the leftover heat of its birth. It is moving across the sky at over 100 kilometers per second, a dead star quietly crossing our corner of the galaxy. 400 light-years is far too distant to ever pose any danger to us. But on the scale of the galaxy, it is practically a neighbor. There may well be others closer that we simply haven't spotted yet, cold and unbeaming, slipping by unseen. Now, most neutron stars live alone. But some of them are born in pairs, two massive stars orbiting each other, and when both die, you can end up with two neutron stars locked in a death spiral. And what happens next is one of the most important events in the universe and one of the most beautiful discoveries of the last decade. Two neutron stars orbiting each other slowly lose energy. They radiate it away as ripples in space itself, gravitational waves, and as they lose energy, they fall closer together. The orbit tightens. They circle faster. Over millions of years, the spiral winds inward, the two dead stars whirling around one another hundreds, then thousands of times a second, until, in the final moments, they are almost touching. Two city-sized balls with the mass of suns screaming around each other at a fraction of the speed of light, and then they collide. When two neutron stars merge, the universe lights up. The collision releases a burst of gravitational waves so powerful that we can detect the stretching of space here on Earth from across hundreds of millions of light years. It releases a flash of gamma rays among the brightest explosions in the cosmos, and it flings out a cloud of neutron star matter, that same impossible material from our teaspoon, into space. And here is where the whole story comes home to you personally. When that neutron-rich matter is thrown out of the collision and released from the crushing gravity that held it, it decompresses, and it undergoes a frenzy of nuclear reactions. In those reactions, the heaviest elements in the universe are forged: gold, platinum, uranium. The elements that are too heavy to be made in the ordinary life of a star are made here, in the violence of two neutron stars tearing each other apart. The cloud of debris from such a collision glows with a light all its own, a fading fireball that astronomers have given a name of its own, a kilonova. And the quantities involved are staggering. A single neutron star merger is thought to forge many times the entire mass of the Earth in gold and platinum alone, flung out into space in one event. Not a vein of gold, not a mountain of it, but worlds worth, scattered across light years in seconds. The gold in a wedding ring, the platinum in a piece of jewelry. The very atoms were almost certainly created in a collision between two dead stars, long before the Earth existed, then scattered across space, drifting for billions of years, gathered into the cloud that became our solar system, and finally pulled up out of the ground and shaped by human hands. Every piece of gold that has ever existed on Earth was made in the death of stars, and a great deal of it in collisions exactly like this. You may be wearing the debris of a neutron star merger right now. For a long time, this was theory. We believed it, but we hadn't seen it. And then, in August of 2017, we did. Detectors on Earth picked up gravitational waves, the trembling of space, from two neutron stars merging about 130 million light-years away. And for the first time, telescopes around the world swung to look at the same event and saw the light from it. They watched the afterglow, and in that afterglow, in the spectrum of the fading fireball, they saw the signatures of freshly made heavy elements, gold and platinum among them, being created in real time and flung into space. A theory that had stood for decades was confirmed in a single night. We watched the universe make gold. That single event answered more than one old question. For decades, astronomers had been seeing brief, intense flashes of gamma rays from across the universe, some lasting only a fraction of a second, and they had argued about what could possibly cause them. When the gravitational waves from that 2017 collision arrived, a short burst of gamma rays arrived almost at the same moment, from the same point in the sky. There was the answer. At least some of those mysterious flashes are neutron stars colliding. One event and three separate puzzles: gravitational waves, the origin of gold, and the source of short gamma ray bursts, all clicked into place together. It is rare for the universe to answer so many questions in a single night. That event has a name now: GWW 170817. It may be the most thoroughly studied collision in the history of astronomy, and it tied together everything we've talked about tonight: the density, the gravity, the matter that cannot survive outside the star. Two neutron stars met, and in their meeting, they wrote the origin of the gold in your jewelry and the uranium in the Earth's crust. It also told us something quieter and more profound. Neutron stars are not just curiosities, not just extreme objects to marvel at. They are part of the machinery that built the world you live in. The iron in your blood came from supernovae. The gold on your hand came from neutron stars colliding. These dead, crushed, impossible objects are not separate from us. They are part of our family tree. The same physics that makes a teaspoon weigh 1 billion tons also, in the end, made the heaviest atoms inside your own body. And we can study all of it from here on Earth because of one final gift these objects give us. They are the universe's most extreme laboratory, and they let us test the deepest laws of physics in ways nothing else can. Here on Earth, there are limits to the experiments we can run. We can build powerful machines, smash particles together, create tiny flashes of extreme conditions, but we cannot make matter as dense as a neutron star. We cannot make gravity as strong as a neutron star's surface. We cannot make a magnetic field 1,000 trillion times Earth's. These conditions are simply beyond us, and they may always be. So when we want to know how the laws of physics behave at their absolute limits, we cannot build the experiment. We have to find it. And neutron stars are the experiment already running, scattered across the sky. Take Einstein's theory of gravity, general relativity. It is the best description of gravity we have, and it makes precise predictions about how objects should behave when gravity is extreme. For most of the 20th century, we could only test it in gentle conditions: the slight bending of starlight near the sun, the tiny drift in the orbit of Mercury. Real, but subtle. To truly test the theory, you need strong gravity, and neutron stars provide it. In 1974, two astronomers, Russell Hulse and Joseph Taylor, discovered something remarkable: a pulsar in orbit around another neutron star, the two of them circling each other closely. This was a perfect natural laboratory. They could time the pulsar's ticks with extraordinary precision and watch how the orbit changed over the years. Einstein's theory predicted that two such massive objects whirling around each other should slowly lose energy by radiating gravitational waves, ripples in space, and that the orbit should therefore shrink at a very specific, calculable rate. So Hulse and Taylor watched, year after year, and the orbit decayed, falling inward by an amount that matched Einstein's prediction almost perfectly. It was the first real evidence that gravitational waves existed at all, decades before we directly detected one. They had confirmed one of the deepest predictions in physics, not in a laboratory, but by watching two dead stars dance. The discovery earned them the Nobel Prize in 1993. That is what neutron stars give us. They are the place where our theories get tested against reality at the extremes, where a number on a chalkboard meets an object weighing more than the sun, and either survives the comparison or fails. So far, against every test these objects have thrown at it, Einstein's theory has held. Neutron stars even gave humanity a kind of address. When we sent our first probes out of the solar system, the Pioneer spacecraft in the early 1970s and later the two Voyagers, we attached a message in case they were ever found by another civilization. And the central feature of that message, the part meant to say where we are, was a map drawn using pulsars. 14 pulsars, each marked with its precise rhythm, arranged like spokes around a central point, the sun. The idea was that any advanced civilization could identify each pulsar by its unique timing, work backward, and find the one location in the galaxy from which all 14 would appear exactly so. Our home address, written in the heartbeats of dead stars. Right now, that map is drifting in interstellar space aboard those probes, carrying the rhythm of neutron stars outward into the dark. And we have started to use that same idea to find our own way. Because pulsars keep time so reliably, and because each one has its own distinct rhythm, a spacecraft far from Earth could, in principle, listen to several of them at once and work out exactly where it is, the way your phone finds its position from satellites overhead. A galactic positioning system built from dead stars. This is not just an idea anymore. In 2017, a NASA instrument on the International Space Station ran the first real test of it, locking onto a handful of millisecond pulsars and using their pulses alone to pinpoint its position in orbit, autonomously to within a few miles. It worked. One day, a probe crossing the empty dark between the stars, far beyond any help from Earth, may navigate by nothing but the heartbeat of neutron stars, the same beacons we once drew onto a plaque to mark our home. The lighthouses would guide the ship. And here is something worth stepping back to notice. Over and over, these objects have forced humanity to invent entirely new ways of seeing. We found the first pulsar because we had only just learned to listen to the sky in radio waves. We discovered neutron stars feeding on companions because we had only just learned to see the universe in X-rays from telescopes lifted above our atmosphere. We caught a stellar core collapsing because we had buried detectors deep underground to catch neutrinos. And we watched two of them collide because we had finally built machines sensitive enough to feel gravitational waves, the trembling of space itself. Radio, X-rays, neutrinos, gravitational waves. 4 completely different senses, 4 new windows onto reality. And neutron stars were waiting behind every single one of them. Each time we opened a new way of perceiving the universe, these dense, dead stars were among the first things we found. It is as though the cosmos kept hiding its strangest objects just past the edge of our senses and rewarded us every time we extended our reach with another glimpse of matter at its absolute limit. And the family of these objects is wonderfully varied once you start to look. There are the ordinary pulsars ticking once every second or so. There are the millisecond pulsars, spun up to hundreds of rotations a second, often by stealing matter from a companion star, which gives them a second life and an incredible stability. There are the magnetars with their galaxy-spanning magnetic flares. There are quiet, isolated neutron stars like our nearest neighbor, just glowing with leftover heat. Some are the lightest that can exist, sitting just above the threshold where a star becomes dense enough to collapse this far. And some are the heaviest, pushing right up against the limit, a little over 2 times the mass of the Sun, as close to becoming a black hole as a neutron star can get without falling over the edge. You might wonder how we can possibly weigh something so far away, and the answer is, once again, that precise rhythm. When a neutron star orbits a companion, its pulses give it away. As the pulsar swings around its orbit, and especially when its light has to pass close by the companion star on its way to us, that companion's gravity delays the pulses by a tiny, measurable amount, bending and slowing the signal exactly as Einstein's theory predicts. From the size of that delay, astronomers can calculate the masses involved with remarkable accuracy. We weigh dead stars by timing how their companions tug at the ticking. The heaviest one measured this way sits at around 2 1/10 times the mass of the Sun, perched right at the theoretical limit. And the current record holder, heavier still, at roughly 2 1/3 solar masses, is itself one of those black widow pulsars, a star that grew to record-breaking mass by devouring its companion. It ate its way to the very edge of becoming a black hole. That edge is the most haunting part. We talked earlier about the knife edge of mass, the line between a neutron star and a black hole. The heaviest neutron stars we have measured are sitting almost exactly on that line. If you could add just a little more mass to them, a fraction more, the neutrons would lose their final stand, and the star would collapse the rest of the way into a black hole, vanishing behind an event horizon, taking its secrets with it. These heavy neutron stars are matter's last stand, the densest configuration that light can still escape from. One step further and not even light gets out. So a neutron star is many things at once. It is a clock accurate enough to test Einstein. It is a forge where the heaviest elements are made. It is a map marking our home in the galaxy. It is a laboratory running an experiment we could never build. And it is a threshold, the last stable object before matter gives up entirely and becomes a black hole. All of that contained in a sphere 20 kilometers wide. All of it expressions of the same single fact we started with, that this is matter crushed to its absolute limit. Which brings us finally back to the teaspoon. Because now that we understand what this material truly is and the violence that holds it together, we can answer the question we began with. What would actually happen if a teaspoon of it came to Earth? Let's do this carefully, step by step, because every stage of the answer tells us something. The first problem is the one we've been circling all night. You cannot actually get a teaspoon of it, not because it's far away, though it is, but because the moment you separated that spoonful from the star, it would cease to be neutron star matter. Remember what holds it together. The neutrons in that teaspoon are crushed against each other by the gravity of more than a sun, pressing in from every direction. They don't want to be that close. Neutron degeneracy pressure is pushing back fiercely every instant. The only reason the matter stays compressed is that the star's gravity is winning, barely holding the neutrons in a state they would never choose. It is a standoff under unimaginable strain. The coiled spring we talked about earlier now lift the teaspoon out. The instant that material leaves the surface, the gravity holding it together is gone. There's no longer a star's worth of mass pressing in, and the neutrons, suddenly free, do exactly what they've been straining to do the entire time. They fly apart, violently. The matter decompresses in an instant, expanding outward with staggering force as all that pent-up pressure is released at once. It would not gently relax into ordinary matter. It would explode. And the energy in that explosion is difficult to overstate. You are releasing the compression of 1 billion tons of material that was being held at nuclear density. The teaspoon would erupt with an energy comparable to an enormous nuclear detonation, perhaps far greater, scattering its neutrons outward in a burst of radiation and newly forming elements. This is, in miniature, the same decompression that happens when neutron stars collide and fling their matter into space. It's the same process that forges gold. A teaspoon of neutron star matter is not a paperweight. It is a bomb that is only disarmed as long as a dead star is sitting on top of it. So the literal answer to our question is almost a trick. If a teaspoon of neutron star matter hit Earth, it would never make the journey as a teaspoon. It would detonate the moment it was freed from the star, long before it got anywhere near us, releasing its energy out in space. The thing the title imagines, a calm little spoonful of star traveling toward our planet, cannot exist. The material is defined by its prison. Free it, and it is no longer itself. But let's be generous and play the game a different way. Suppose by some impossible trick of physics, you could keep that teaspoon compressed. You could carry 1 billion tons in a sugar cube, stable, in your hand. What then? Then you would be holding an object with the mass of a small mountain, concentrated into a point. And its own gravity, while nothing like the full stars, would still be significant for its size. But the real trouble is what 1 billion tons does when you let go of it. It would drop, and nothing could hold it. It would fall through your hand, through the floor, through the rock beneath the building, sinking into the earth as if the planet were made of mist. 1 billion tons in a tiny volume would punch downward under its own weight, slicing through ordinary matter, which, remember, is mostly empty space. And it would not stop at the surface. It would plunge toward the center of the Earth, oscillating back and forth through the core, passing through solid rock as easily as a stone falls through air. Our entire planet would be, to this object, almost no obstacle at all. It would not destroy the Earth in a flash, but it would be a permanent, unstoppable passenger, falling endlessly through the world, 1 billion tons that the planet simply cannot catch. There is something almost philosophical hiding in that image. The reason the teaspoon would fall straight through the Earth is the very same reason we started with at the beginning of the night. Ordinary matter is mostly empty space. A planet seems solid to us only because we, too, are made of the same loosely built atoms, and our emptiness pushes against its emptiness. But to a piece of matter where the emptiness has been erased, the Earth is barely there at all. The teaspoon would experience our entire world the way we experience a thin fog. It would prove, in the most dramatic way possible, that everything you have ever thought of as solid is in truth almost nothing, held apart by forces waiting. The neutron star is what the universe looks like when those forces finally lose. That, though, is a fantasy, because the matter can't stay compressed. So let's ask the bigger, fairer version of the question. Forget the teaspoon. What if an entire neutron star came toward Earth? Here, at least, the physics is honest, because a whole neutron star can exist on its own. And the answer is that it would never need to touch us to end us. Long before a neutron star reached the Earth, its gravity would take hold of our planet and the entire solar system. It would disrupt the orbits of the planets, fling worlds out of their paths, and tear at the Earth with tides so extreme that our planet could be pulled apart, stretched, and shredded by the difference in gravity between the near side and the far side. The oceans would rise to meet it. The crust would crack. We would be unmade by gravity alone, gently in the language of physics, catastrophically in every way that matters, without the neutron star ever making contact. And it would not be sudden. Long before the end, we would see it coming in the slow derangement of everything familiar. The tides would begin to climb higher each day as the approaching gravity pulled harder on our oceans. The orbits of the planets would loosen and warp. The Earth itself would start to flex, groaning under the growing strain. The difference in pull between the near side and the far side stretching the whole planet like dough. There would be no impact to brace for, no moment of collision, just a steadily tightening grip from the dark, an object the size of a city pulling a world apart from across the gulf of space, simply by being what it is. The danger was never that it would hit us. The danger is everything it does without ever needing to. So, in a strange way, the teaspoon and the whole star give the same lesson. The danger of a neutron star is never really about impact, it's about the gravity. The teaspoon's matter is held by gravity and dies without it. The whole star kills with gravity from a distance. Everything about these objects comes back to that single, overwhelming force, pressing mass into a space too small to hold it. And then comes the reassurance which you have surely been waiting for and which is real. None of this is going to happen. The nearest neutron star is 400 light-years away, and it is not coming toward us. There is no neutron star on a path to the solar system, no spoonful drifting our way. The galaxy is vast and mostly empty, and the odds of a neutron star ever passing close to us are vanishingly small over even billions of years. You are completely safe. This is a thought experiment, a way of feeling the scale of these objects by imagining them where they could never be. The real neutron stars are far away, drifting through the dark, harming nothing, simply existing at the edge of what matter can endure. But sit with the strangeness of it for a moment. The reason a teaspoon of this material is so dangerous is not that it's poisonous, or sharp, or hot, though it is unimaginably hot. It's that it is wound tighter than anything else in the universe. It is matter pushed so far past its natural state that it can only be held by the weight of a star. And the moment that weight is lifted, it lashes back. There is something almost alive in that tension. 1 billion tons coiled in a spoon, straining every instant to be free. We began tonight with a question about danger. What would happen if this matter struck the Earth? And we followed it to its strange conclusion. But the longer you sit with these objects, the less they feel like a threat, and the more they feel like a kind of revelation. Because a neutron star is one rung on a ladder, and seeing the whole ladder is where the real awe lives. When a star dies, the kind of corpse it leaves behind depends entirely on its mass. There are 3 possible endings, and they form a sequence, each one denser and stranger than the last. A small or medium star, like our Sun, ends gently. It sheds its outer layers and leaves behind a white dwarf, the cooling ember of its old core. A white dwarf is dense by ordinary standards. It packs roughly the mass of the Sun into something about the size of the Earth. A teaspoon of white dwarf material would weigh several tons, about as much as a small car. There is one quite close to us, in fact. The brightest star in our night sky, Sirius, has a tiny white dwarf companion, Sirius B, less than 9 light-years away, an Earth-sized ember with about the mass of the Sun, quietly cooling. That sounds extreme, and it is, until you set it beside what comes next. The white dwarf is held up by the stubbornness of its electrons, the same degeneracy pressure we met earlier, refusing to be crowded. And as long as the white dwarf stays below about 1.5 times the mass of the Sun, the electrons hold, and it survives, slowly cooling for billions of years. But push past that limit, the limit named after the physicist who calculated it, and the electrons lose. They are crushed into the protons, and the star collapses to the next rung, a neutron star. A teaspoon now weighs not tons, but 1 billion tons. The size drops from Earth-sized to city-sized. The electrons have given up, and only the neutrons remain, holding the line with their own fiercer stubbornness. And then there is the final rung. Push past the neutron star's limit, somewhere around 2 to 3 times the mass of the Sun, and the neutrons lose too. Nothing in nature can hold the matter up any longer. The collapse continues past every form of resistance, and the object disappears behind an event horizon, a black hole. The teaspoon question stops having an answer at all, because there is no longer a surface to take a teaspoon from. The matter has fallen out of the universe we can describe. So the neutron star sits in the middle of this ladder, and it is the most extraordinary rung of the 3. The white dwarf is held by electrons. The black hole is held by nothing, having surrendered completely. The neutron star is the last object that fights back and wins. It is matter making its final stand against gravity, holding itself together by the slimmest margin, at the very edge of what is possible. One rung down and it would be merely dense. One rung up and it would be gone. The neutron star balances on the knife's edge between the two, and that is exactly why it is so strange. It is the densest thing you can still call a thing. The most extreme object that still has a surface, a shape, a place where you could, in principle, rest a spoon. That ladder, electron, neutron, nothing, is in a way the whole story of gravity, written in 3 objects. And we are only here to see it because our own star sits safely at the bottom of it, destined for the gentlest of the 3 endings, billions of years from now. There's a thought about neutron stars that I find genuinely calming, in the way only deep time can be calming, and it has to do with how long they last. A neutron star is born scorching hot, 1,000,000 degrees or more at the surface, and from the moment it forms, it begins to cool. But it cools with extraordinary slowness. It has no fuel left to burn, no fire inside it. All it can do is slowly radiate away the heat it was born with, leaking it into space across unimaginable spans of time. After 1,000,000 years, it is still hundreds of thousands of degrees. After hundreds of millions of years, it is still glowing faintly. A neutron star does not cool the way a cup of tea cools by morning. It cools the way a continent might, over ages that dwarf the history of life on Earth. And it keeps its spin and its magnetism for a long, long time as well, gradually slowing, gradually fading, but lasting through it all. A neutron star formed near the beginning of the universe could still be out there now, dimmed but intact, having outlived nearly everything around it. Now follow that forward. The stars we see in the night sky will not last forever. Stars are born, they burn, they die. The universe is steadily using up its supply of gas to make new ones, and one day, in a future so distant the numbers lose meaning, the last star will form, burn through its life, and go dark. The era of starlight will end. The sky everywhere will fall black. But the neutron stars will still be there. Long after the last star has died, these dense remnants will remain, drifting through a darkening cosmos, slowly, slowly giving up the last of their heat. They are among the objects that will outlast the age of stars itself. In the deep future, when the galaxies have gone dark and cold, the neutron stars will be some of the last solid, structured things left, the final embers of a universe that has burned through its fire, quiet, dense, patient beyond comprehension. How long they last in the very end may depend on the deepest laws of physics, the ones we have not fully tested. Some theories suggest that over timescales so vast, they make the current age of the universe look like an eye blink. Even the protons inside ordinary matter might slowly decay. And if that is true, then over unimaginable spans, even neutron stars would eventually crumble away to nothing. Other theories say protons last forever, in which case these dense cinders might simply persist, cold and dark, for as close to eternity as anything in the universe gets. We do not yet know which is true. But either way, the neutron stars are among the longest-lived structures reality will ever produce. Whatever the final fate of matter turns out to be, these objects will be among the last to meet it. There is something restful in that, I think. We tend to imagine these objects as violent, and at their birth, they are. But their long life is the opposite of violent. It is stillness on a scale we can barely hold in the mind. A neutron star spends almost its entire existence doing nothing at all, but cooling, turning, and waiting, holding 1 billion tons in every spoonful, asking nothing of the universe, simply enduring. Some of them have been doing it since long before the sun existed. Some of them will still be doing it long after the sun is gone. When you picture one now, you don't have to picture the explosion. You can picture the long quiet afterward. A perfect sphere, 20 kilometers wide, turning gently in the dark, glowing with the last warmth of a star that died before the Earth was born, and carrying on calm and unbothered toward a future longer than the one that came before. It's worth remembering how recently all of this entered human knowledge. We did not always know these objects existed. For almost the entire history of our species, no one had any idea that the universe could fold matter this tightly. The idea was first put down on paper in the 1930s when a handful of physicists working with the brand new discovery of the neutron dared to suggest that a star might one day collapse into a ball of them. The neutron itself had only been discovered in 1932, and within just a couple of years, 2 astronomers, Walter Baade and Fritz Zwicky, were already proposing that a supernova might be the moment an ordinary star transforms into one of these tiny, dense remnants. A few years after that, in 1939, the physicist Robert Oppenheimer and a colleague worked out the first detailed mathematical model of such a star, even calculating the rough limit beyond which it would have to collapse into a black hole instead. It was a fringe idea, almost science fiction at the time, a calculation with no object to attach it to. For more than 30 years, neutron stars existed only as a possibility in a few equations. Many scientists doubted they were real. There seemed no way to ever detect something so small and so far away. And then in 1967, the accidental discovery of that first pulsar, a bit of scruff on a roll of chart paper, proved the equations right. Within the lifetime of people still alive today, neutron stars went from a doubted theory to an observed fact. Everything we now know, the spinning, the magnetism, the mergers, the gold, all of it has been learned in a span shorter than a single long human life. Your grandparents were born into a world that did not know neutron stars were real. We are living through the first chapter of our understanding of them, and that chapter is far from finished. There is a great deal we still do not know. We do not know for certain what lies at the very center of a neutron star. We've talked about the possibility of free quarks, of an exotic soup of fundamental particles unlike anything else, but it remains unconfirmed. We do not know the precise point at which a neutron star becomes too heavy and collapses into a black hole. We know roughly where that line falls, but not exactly, and pinning it down would tell us something profound about the nature of matter itself. We are not even fully certain whether some of the objects we call neutron stars might actually be something stranger, entire stars made of quark matter, denser still. These are not small gaps. They sit at the foundation of physics, the question of how matter behaves when you push it to the absolute limit. And the answer is hidden inside objects we can never visit, never sample, never crack open. We can only watch them from across the galaxy, gathering their light and their rhythm, and slowly, patiently, narrowing the possibilities. Every neutron star merger we detect, every pulse we time, every X-ray we catch, sharpens the picture a little more. We are reading the most extreme matter in the universe at a distance of thousands of light years by its faint signals alone, and somehow, piece by piece, it is working. There is something humbling in that and something hopeful. The teaspoon we started with, the billion tons we can never hold, is also a question we are still answering. These objects have not given up all their secrets. They are still out there, turning in the dark, holding the truth about matter at its limit inside a sphere we will likely never reach. And we are still learning to listen. And we can listen in a way that is stranger and more beautiful than you might expect. The pulses from a pulsar arrive as radio waves, invisible and silent. But radio waves can be turned into sound, the same way a radio in your car turns invisible signals into music. And when astronomers take the steady beat of a pulsar and convert it into something we can hear, the result is haunting. You hear a rhythm, a regular tick, or a low hum, or a rapid drumming, depending on how fast the star is spinning. The slow pulsars sound like a heartbeat or a distant drum, patient and even. The fast ones, the millisecond pulsars, blur into a smooth, eerie tone, hundreds of beats a second running together into something almost like a held note. Sit with what that sound actually is. You are hearing the rotation of a dead star. Each tick is one full turn of an object more massive than the sun, the beam of its magnetic pole sweeping precisely across the Earth, again and again and again. That rhythm has been keeping perfect time for millions of years, long before there was anyone here to hear it, and it will keep that time for millions more. It is, in a sense, the oldest and steadiest drumbeat in the universe, and it is coming from the crushed heart of a star that exploded before our species existed. So let yourself picture it from a safe and impossible distance. You are somewhere out in the dark, far from any danger, watching one of these objects turn. You cannot see much, just a faint point of light, no bigger than a city, glowing with the leftover heat of its birth. But every fraction of a second, a beam sweeps past you, a silent pulse of energy, regular as breathing. The star is spinning faster than you can follow, holding more mass than the sun, wrapped in a magnetic field that could unmake you, smoothed to a sphere more perfect than anything ever made. And it asks nothing of you at all. It simply turns and ticks and shines and waits exactly as it has since the universe was young. That is the true face of a neutron star, not the explosion that made it, not the disaster of the teaspoon, just this, a small, dense, silent thing keeping perfect time in the dark. And by listening to not just one of these clocks, but to many of them at once, we have begun to sense something no one ever expected we could feel. Scattered across the galaxy are dozens of millisecond pulsars, each one ticking with that incredible clock-like steadiness. Astronomers have spent years timing them, all of them, together, watching for the tiniest, most coordinated wobble in their rhythms. Because if a gravitational wave, a ripple in the fabric of space itself, were to roll slowly through our part of the galaxy, it would very slightly stretch and squeeze the space between us and those pulsars. And that stretching would show up as a faint, shared pattern in when their pulses arrive. A little early here, a little late there, in a particular signature spread across the whole sky. In 2023, after 15 years of patient timing, several teams of astronomers announced that they had found it. Using dozens of pulsars as buoys floating on the sea of space, they had detected a low, constant rumble of gravitational waves washing through the galaxy. The likely source is almost beyond imagining. Pairs of supermassive black holes, each one millions or billions of times the mass of the Sun, slowly circling each other in the hearts of distant galaxies, shaking the fabric of the universe as they spiral together. And we sense that shaking by watching dead stars flicker. Think about what that means. We turned a scattering of neutron stars, the crushed corpses of giants, into a detector the size of the entire galaxy. The most precise instrument humanity has ever used to feel the trembling of space-time is built not from steel and glass, but from the rhythm of stellar ghosts. The same impossible density that fills our teaspoon also makes these objects steady enough to register a ripple in space that shifts their timing by less than a millionth of a second. The strangeness and the usefulness are the same thing. Because the matter is crushed so perfectly, the clock is flawless. And because the clock is flawless, we can hear the universe move. Now, before we let the night settle, hold the spoonful in your mind one more time with everything we now know packed into it. A teaspoon, the kind of thing you'd stir into a drink without a thought, and inside it the weight of a mountain, the weight of all 8 billion of us gathered together. A piece of matter so dense that the emptiness inside ordinary atoms has been completely erased, so heavy that lifting it is impossible, so tightly wound that it would explode the instant you set it free. You cannot really picture 1 billion tons in a spoon. I can't either. The human mind has no shelf to put that number on. But you don't need to picture it perfectly to feel the awe of it. You only need to know that it is real, that somewhere out there, right now, there are hundreds of millions of objects made entirely of this matter, turning silently in the dark. The universe did not make these as a curiosity, or a threat, or a riddle for us to solve. It made them simply because that is what happens when a great star dies, and gravity is allowed to finish what it starts. They are a natural consequence of the rules, and those same rules, the ones that crush a star into a city-sized sphere, are the rules that built you, and the ground beneath you, and the gold you might wear, and the iron in your blood. Now, as we come to the end of our journey tonight, let the scale of it settle over you gently, the way sleep settles. We started with a simple, almost frightening question. What would happen if a teaspoon of a dead star came to Earth, and the answer turned out to be a doorway? It led us through the death of giants and the birth of the densest matter in existence. It led us down through crust stronger than steel and oceans of frictionless neutrons. It led us across the galaxy to colliding stars forging gold, to dead stars with planets, to a guest star, watched in daylight 1,000 years ago that is still turning in the heart of a glowing cloud. 1 teaspoon, and inside it, almost everything. That is what these objects do, if you let them. They take something small, a spoonful, a number, a flicker of light, and they open it until you are looking at the whole structure of the universe through it. They remind us that matter has limits and that the universe lives right at the edge of them. They remind us that the most violent events leave behind the quietest, steadiest things. They remind us that we are made of the debris of dead stars and held together by the same force that crushes them. And they remind us that even the most extreme corners of reality can be reached, not with spacecraft, but with patience and careful attention and the willingness to keep listening. Thank you for spending this time with me tonight, drifting out to the neutron stars and back. If these slow journeys through the universe bring you a little calm at the end of the day, you can help others find the same quiet by leaving a like or by subscribing so the channel can keep making them. It genuinely means a great deal. And now, picture it one last time and let it carry you down into sleep. A perfect sphere 20 kilometers across, turning gently in the dark, glowing faintly with the last warmth of a star that died before the Earth was born, holding 1 billion tons in every spoonful, asking nothing, harming nothing, simply keeping its slow and patient time. It was here long before us. It will be here long after. And tonight, from unimaginably far away, its faint and steady rhythm is still reaching us like a heartbeat in the deep. Rest well, and we'll travel again soon.